So when we talk about database query optimization, especially when it comes to SQL databases, the first thing that comes to our minds is indexes, right? They're the most fundamental tools when it comes to speeding up our queries and reducing load on the I/O. But there are also instances where an index can really slow down your query if you're not implementing it properly. Sometimes the index itself can actually be what causes the issues. So we're going to be looking at a query today, and this is a query that I'm running on a Stack Overflow database dump, which is available online. It has around, my dataset has around 3 million posts, so 3 million rows in the post table and around 300,000 users in the user table. So this is a query. Let's take a look at this. And this query is pretty simple. We want to find the latest posts that are after a specific date. In this case, it's January 1st of 2008. So we want the latest 20 posts after this date, and alongside the posts I want the username of the user and his account ID. So it looks like a pretty standard query when you look at it from a bird's eye view. You're just doing a very simple select. You do an inner join on the users table on the user ID with account ID, and I'm filtering by removing everything that has empty titles. And also the creation date is, everything after this date, and order by this column and limit it to 20. So right now there are no indexes on the fields that we are filtering by. So I do not have any index on title. I do not have any index on the creation date, nor on anything. I don't have an index on anything, So let's run this query and see how it performs. And this is the query actually, it's nothing too special. You have a bunch of posts, right? And then you have it sorted by the creation date. So you have all of these. Now let's try to analyze this query by using explain analyze. And let's see what we get. Voila. So if we take a look at this, we can see that the total execution time is 307 milliseconds, right? Which is not that bad considering we have so many tables here, so many rows here for the table, right? So there's a whole lot of rows here, and we have 3 workers. So 3 workers each are taking 360,000 rows. So it's taking around 1 million rows in this query. So it's doing a sequential scan on this table and then doing a sequential scan on the users table. So they're reading everything from the disk, and then the users table is then being built into a hash table, right? So then using the hash table, it's doing a parallel hash join. So it's taking every single row from this posts and then just doing a probe, and this hash table is in memory. So it's really, really fast. But this query itself is being limited by the disk. And the way we can judge that is if we take a look at the timestamps. So the last row from this scan is returned after 158 milliseconds since the start of this query, which is actually quite a long time. Because after that, the rest of the time is being spent by coordination, right? So scheduling by the gather merge, because the workers have to report to the coordinator before they can terminate themselves. So it's relying heavily on the disk. And when you think about optimizing this query, the first thing that comes to your head is, okay, why not we run an index? Why don't we create an index, right? We index the creation date, and we can do that. And another easier option, another more optimized option would be to also make it into a partial index. So rather than having the entire posts table indexed by the creation date, index it only for the ones where the title field is not empty. So we want to have a partial index. So let's try doing that. That should work out pretty well since we're reading a million rows here. So we can do create index on posts by creation date where title is not empty. Create an index. So now that we have an index, we should be having a pretty fast query. At least we expect to have a fast query. So this 306 milliseconds should drop down to something like, I don't know, maybe 10 milliseconds. So let's run this query and see what happens. And it's taking a long time, as you can see. And look at that. This query is taking 4 seconds. It went from around 300 milliseconds to literally 4 seconds just for this entire query. And there are so many reasons for it, right? There's not a single culprit. When you take a look at this query plan and you go through each step one by one, you will understand why it's taking 4 seconds for me to receive only 20 rows. And it's actually quite simple when you take a good look at it. So let's actually start off with, the start. We have limit, of course. We're getting only 20 rows. And the biggest change here is, if you noticed, we do not have any hash joins. So the hash join got replaced by a nested loop, right? That means there is no hash tables here. And we have materialize instead of having a hash join and a hash table. The good thing is the posts table, which had millions of rows, is not part of a full sequential scan. It's scanning only 83 rows per worker, so we get around 250 rows total. So for getting 20 rows, it's scanning 250 rows from the posts table. Okay, that sounds very good. Then where is it going wrong? Why are we taking this long for this query to execute? Well, you take a look at this. There's actually multiple issues here. This query is slow. I'm just going to tell you right now and then explain. This query is slow because of this nested loop join. And you can see this join filter here. And this inner side of the query that is being joined, right? So the inner table, which is the users table, this is being stored on the disk, right? And here's how a nested loop actually works. So a nested loop is kind of like the same concept in programming as well, right? So think of this as, okay, for each row in posts, so if it's like a for loop, then inside the for loop, you're going for each user in users. So you're basically looping over or going over the entire users table for every single row in the posts table. And this is just diabolical, because think of it like this, right? I mean, this is actually what's happening. We have 83 rows per worker, so 250 rows total. And the total number of rows in, the users table is around 300,000. So if we do a multiplication, okay, 300,000 users, right? And then around 250 rows, then if you multiply that, the total number of comparisons you're going to get is something around 73 million. Okay, so this nested loop, what it's doing is it's going over every single row in the posts and then going over every single row in the users table and then trying to do a join to see if the joins match. And that's causing a total 73 million or something like that. My math could be off. Around 73 million join checks, which is just insane. And this could be optimized, and Postgres did try to optimize this, right? We can't say that the Postgres planner is stupid, even though it kind of looks like it is, but it did try to optimize this. And the way it tried to do that is using Materialize. So Materialize is basically kind of like a caching mechanism, right? Because the query planner knows that, okay, for every single row, I'm going to have to go over the entire users table, right? Because that's how the nested loop works. And since I have to do that, why not read the entire users table once, run a sequential scan on the users table, and then cache it, right? Why not cache this so that it's easy to do so? But here's the problem. Materialize tried to cache it in RAM, but there's not enough working memory for that, which is why you can see the storage is in disk. So even though Postgres tried to cache the output of the users table, it ended up caching it to the disk. So even though we can say that there's a quote-unquote cache, this is still not performing on the same level as a RAM cache, right? It's still on the disk. So this query is still very IO bound. And when you're doing around 73 million checks, I think you can kind of get the idea of why it's taking 4 seconds to finish this entire query. Because this is on the disk, it's a temporary file on the disk for as long as the query runs, and that's what's causing the issue. And now you may ask the question, like, okay, then why are we using nested loop in the first place? Like, why can't the Postgres planner just use the hash table for the users table, just like it did, but utilize the posts table index? Like, why doesn't it do that? Well, the reason is because of this limit. This limit, along with the index, is telling Postgres to use the nested loop. And the way it works is basically quite simple, actually, maybe not trivial, but simple, is that limits in Postgres mean that, okay, it tells the query planner that, okay, since I'm using an index, now this has to be limits with index, since I have an index on the creation date column, which means, and indexes are always ordered, right? So I have this index on the creation date column, and I'm ordering by the creation date column. So that means if I can scan only the 15 rows, I only need 15 rows. Like, after scanning 15 rows, I can just be done with the query, right? You know, I don't need to do a full sequential scan. I can just scan like 15 rows or maybe a bit more if the joins do not match. That's why it goes for 250 rows, because the first 15 rows do not satisfy the 15 limit after the join filtering. But once that is done, right, it doesn't need to do anything. It can just stop the query. But the thing is, for a hash join to work, I mean, you know, hash tables exist when you want a hash join. But for the hash joins to work itself, it needs to run the query completely rather than just stopping early. Because limit tells you that, okay, you can stop the query early if you just have the data. But hash joins require you to do a full sequential scan. You cannot just stop early. Because this is because of the index. Since you have the index, limit is saying, okay, the index just gives us, you know, like, we can just find the latest 15 and be done with it. Without the index, limit doesn't know how it's ordered, so it's just going to run an entire sequential scan, and that's when it can try using the hash table, which is quite performant, right? Hash tables are boring, but they work. So that's the main reason why we are having this Materialize read the entire thing from disk and store this on disk. So the main culprit here isn't our posts table. The culprit is both the Postgres query planner or the PostgreSQL engine overall. It has limitations. If it didn't have limitations, we could just be using the hash joins, even with the limit and indexes. But it has limits. So And another culprit is, this thing here. And you see the number of rows removed by the join filter. You have 73 million combinations. From that, 24 million are just gone. The amount of work loss is just insane in this query. So how do you solve this, right? Enough yapping about, where the problem is, even though I wanted this video to be a deep analysis of the entire thing. So how do you solve this, right? Let's get back on track. We need to somehow optimize this scan. So rather than doing a sequential scan on the users table, if we can somehow optimize this, we can hope to have a very fast query. Right now it's taking 4.1 seconds. We can try adding an index to this table, the users table, and specifically on the account ID column, because this is what the join filter is, right? The nested loop is matching the join on this column. Let's try adding an index for this. So we can try doing this, create index on users, and we can do account ID. Let's try that. Created the index. Now let's run this query, see how fast it runs. And would you look at that? From 4 seconds to 0.355 milliseconds. Okay, I'm going to do some math and let me see how fast it is. Okay, so this is apparently 11,000 times faster than what we had before. This is 11,000 times faster. We had 4 seconds, 4.2 seconds. And now this is 0.3 milliseconds. We can have indexes. Indexes are very important, right? You're just looking through a binary tree rather than just going through the entire heap and running a sequential scan, right? You don't need to do that. Just look through the index. But having indexes along with limits makes the query planner act very funky. So if you're using a join here, like how we are doing a join on the users table, make sure that for any nested loops which have an inner join, that inner join is indexable or indexed, I don't know how to say it, is indexed on that join column, or else you're going to face issues like this. So yeah, I hope that explains it. And that is it for this video. Thank you for watching. If you want more videos like this, do let me know if you want me to explain something else. But this was really interesting because I was just working with this data set, just trying to run some queries and analyze some query performances, and I just came across this and thought, okay, why not make a video on this? Maybe this will be insightful for those who are not that much into database internals. But yeah, I will see you guys in the next video. Bye.